So for our last example of dynamic programming for this week, we look at the problem of efficiently multiplying a sequence of matrices. So as you probably know, to multiply two matrices A and B, you need compatible dimensions, right? So if we have A and B, then we need that the number of columns in A must match the number of rows in B. So we have m times n matrix A and an n times p matrix B, and the final matrix is going to be of times m times p. It will have the same number of rows as A, the same number of columns as B. And the way you compute the product AB, so if I want the ijth entry in AB, then I will take the ith row in A, okay, and I'll somehow multiply it with the jth column in B. So I will take the first entry here, the first entry there. So I'll take AI1 and B1j, multiply them, AI2, B2j, multiply them, finally AIN, BNJ, multiply, add them all up. So this takes order n steps, right? Because I'm computing order n pairwise products and then adding them up. So therefore I have to compute finally m times p entries. Each entry requires a linear order n amount of work. So the total cost of multiplying two matrices in terms of basic arithmetic operations is of the order of m times n times p. So this is the basic fact that we need for the problem. So now the concern is not computing the product of two matrices, but computing the product of three or more. So supposing I want to multiply three matrices A, B and C. At a time I can multiply any two. So either I have to multiply it as A times B, get a intermediate matrix AB and then multiply it by C, or I can do B times C and then multiply it by A from B. So matrix multiplication is not commutative. We don't have this in general, okay. So it is important that the order is the same, but within that, in which sequence I do this simplification doesn't matter. So it's associative. I can bracket it by as A times B followed by C or A times B followed by C. Either way I have to do two matrix multiplications, okay. And what associativity means is that the answer will not change. The final product will remain the same. But what is interesting for us now is that the complexity of computing the answer can change depending on which order I do it. Whether I do it as A times B followed by C, or first I do B times C and then I pre-multiply by A. So let's look at a very trivial example. Right? So I have three matrices of this kind. So A is a matrix which looks like this. Right? It has one row and 100 columns. B is a matrix which looks like this. It has 100 rows and one column. And C is again a matrix which looks like this. So this is my A, this is my B, and this is my C. Okay. So now supposing I do B times C first. If I do B times C, what happens is this 100, okay, will now blow up and I will get a big matrix which is 100 by 100. Because I'll have 100 rows here and 100 columns there. Right? And so the final thing is going to be number of rows in B and number of columns in C. So the B times C matrix is actually 100 by 100. And how many steps does it take? It takes m into n into p, which is 100 into 1 into 100, which is 10,000 steps. Now I have A which is 1 by 100 and B which is 100 by 100. So I'm going to produce something which is again 1 by 100, but I'm going to take 1 into 100 into 100, right? Because m into n into p is another 10,000. So together this particular sequence requires 20,000 steps. If I did it the other way, on the other hand, if I computed this product first, then I will collapse it to a simple 1 by 1 matrix, because number of rows here is 1, number of columns is there. Right? So AB is a 1 by 1 matrix and it takes only 100 steps to compute. And now again I have a 1 by 1 times a 100 by 1 matrix. So again it takes only 100. So this takes only 200 steps. So you can see that there can be a dramatic difference in the complexity depending on whether you bracket it as AB followed by C or A followed by BC. So in general we'll have a sequence of n such matrices, right? So M1, M2 up to Mn, and their dimensions will be R1, C1, R2, C2 up to Rn, Cn, number of rows, number of columns. The dimensions will be given to us so that they can be multiplied. Remember that all we need, assuming the entries of course can be combined by sensible multiplication addition operations, what we need to be able to multiply two matrices is the dimensions should match. So we are guaranteed that the column of each matrix, size number of columns is equal to the number of rows of the next matrix. So that product is well defined. Okay? And our goal is to find an optimum way to compute this product. What is the sequence of basic operations of multiplying two matrices together that I need to perform to get the minimum overall cost? And this is equivalent to finding an optimum way of bracketing. So remember when I did A times B times C, the choice was whether to put the bracket like this, okay, or to put the bracket like this. Now in general, if I give you now A times B times C times D, then you can do many things, right? You can do A, B, C, D and then multiply. Or you can do C, D, then B, C, D, then A, B, C, D. Or you can do A, B, then A, B, C, then A, B, C, D. Okay, so there are many different ways in which you can partially compute pairs of products of pairs and build up the whole thing. So we want to find the optimum way to do this. So let's try and identify the inductive structure in this problem. So our goal is to compute this long product M1 to Mn. But remember that at every stage we can only multiply two matrices at a time. So at the final stage, we would have multiplied two such matrices. Now we can regroup by bracketing, but we cannot reorder. So when we did the final stage, we would have had two groups, right? So we would have done some product from the left to the midpoint and some product from the midpoint to the end, right? So for some k, we would have computed M1 to Mk and Mk plus 1 to Mn. In the first part, after doing all this, we'll have as many rows as M1 and as many columns as Mk. So it will be R1 times Ck. Second one will be Rk plus 1 to Cn. Right? And we know that Ck is going to be equal to Rk plus 1. So that these two can be multiplied together. Right? So the final cost is going to be M into N into P, which is R1 into Ck into Cn. So we know how much the last step takes. Assuming that it was broken at Mk, the last multiplication costs us this much. Now to get the total cost of doing it with this particular choice of k, we have to get the cost of computing M1 to Mk and Mk plus 1 to Mn. Right? So we have this final situation and now we have these two subproblems. Right? So we have these two subproblems. So the total cost is going to be the cost of the first subproblem, however much it takes to compute M1 to Mk, however much it takes to compute Mk plus 1 to Mn, plus the cost of the last step, which is to multiply these two subproblems after they produce one matrix each, to multiply those two matrices together. But we have said that this k could be anywhere between 1 and n. So which k should we choose? So the spirit of these kind of problems that we have been seeing, these inductive things, is that we don't try to make a choice. Okay? We say we have no idea in advance which k is good. So we just try out all possible k's and take the best one. In this case, the minimum one. In other words, the cost of multiplying M1 to Mn in terms of total number of operations should be the minimum value of k between 1 and n. It has to be strictly less than n because the second part will be Mk plus 1. Okay? So between 1 and n of multiplying the matrices 1 to k, multiplying the matrix k plus 1 to n, and adding the cost of the last multiplication. Okay? So now in turn, if I look at this for example and I break it up, it will break up at some intermediate point mj. Right? So I'll have some mj plus 1 to mk. Right? So I would get arbitrary segments from 1 to n as my subproblems. So a natural thing is to define the inductive structure on an arbitrary segment from mi to mj, where of course I is less than j. Okay? So we want the minimum value for any k in the middle, k between I and j, of going from mi to mk and then from mk plus 1 to mj, and the cost of the last multiplication, which is r1 into ck into cj. Okay? So as before, we will just use the index. So instead of writing cost of m1 cross m2 or whatever, we will write ij. Cost of ij is the cost of multiplying mi to mj, that whole sequence. So let's look at the final inductive form of the equation that we need to compute. So the base case is when we are looking at a sequence of length 1. Right? So if we are computing, for example, M1, M2, M3, M4, then one possibility is that I break it up as M1 times M2, M3, M4. Now if I am doing this breakup, then the cost of doing M1 is nothing, because if I am computing from 1 to 1, I am doing no multiplication. So the cost of II is 0. And then otherwise, I use the recursive formulation we had before. We take the minimum value for k ranging from I but not strictly less than j of the cost to I to k, cost k plus 1 to j, and Ri times Ck times Cj. Okay? And of course, we will only compute this when I is less than or equal to j. We'll never want to compute it when the index j is smaller than I. Now it's instructive to check what happens when I do something like cost I plus 1. Okay. So what this will say is that I want to take mi plus 1. Now my only possible value for k, so k should be between I and strictly less than I plus 1. So that means the only possible value for k is I. So this will break up this thing as mi to mi and mi plus 1 to mi plus 1. Right? And then inductively those will give me cost 0, and then I will only get the cost of multiplying this pair, which will exactly come out of this term. Right? So there is no problem with this base case. We only need the base case when the two indices are exactly equal. So now, as before, we will have this matrix to fill up. Because we have this is not used, because we require, so I is going this way, so we have the first index going this way and the second index going that way. So we basically never need to look at values where the ending point is before the starting point, so we only need to look above the diagonal. Right? And now if we are trying to compute the position ij, then we will need cost ik, that is in this row we will need values between for smaller values than j, and we will need values of the form jk, kj rather, right, in this column. So we will need the values below and to the left with respect to the diagonal. Right? So one way of doing this is to fill up this way, so that wherever we fill up, we have the values below already, and we also have the values to the left. Okay? So we will fill up this matrix from bottom to top. You can also fill it up by diagonal, but it's very painful to program it. So it's better to do it in either row by row or column. So you could also start like this, right? You could also do it this way, so that wherever you start, you have the values below and to the left. Okay? So you start from the diagonal and work right or up. So either you start at the top left and work down the diagonal, and each column you do bottom to top, or you start in the bottom right and work up the diagonal, and each row you do left to right. Okay? So either of these will work. So here is a pseudo code for that. So we first initialize a diagonal to be 0. Okay? And now we do what we said before, is that we start all the columns. Okay, so this should actually be from column. So column 1 we don't have to do because that is the diagonal element. So we started column 2 onwards. Right? So 2 to n. Then for every row starting from the diagonal up to the top row, we now need to compute this minimum. So we initially assume that the value to be filled there is infinity. Now infinity could just be the product of all the dimensions plus 1, because you know that that's not going to, the cost is not going to exceed that. So you can choose a large value. And what you do is now you check for each value of k, you find that inductive thing. You look at r to k, k plus 1 to c, and then r times ck times cc. Okay? So you look up this particular value, which is the inductive thing, and then if it is smaller than the value you have seen so far, so this is basically computing that min over k. By setting it to infinity and then looking and updating every time. So this is just a direct implementation of the recursive, of the inductive thing, and it's just enumerating the subproblems in a way which respects the dependency as we have seen before. So one interesting thing to note is that we are filling up an order n square table. Now when we looked at longest common subsequence or edit distance, we said that the complexity of the problem time wise was exactly the complexity of the size of the table. We had an m times n table, it takes m times n time to fill it up, because in those two problems we were filling up each entry looking at exactly 3 neighbors. So we had a constant lookup. Now here what happens is that when I'm above the diagonal at some distance, in order to fill this entry, I need to scan this row and this column, right? So the amount of time it takes to fill one entry in my matrix could be linear. In the extreme case, when I'm very far from the diagonal, I could be spending order n time to fill that entry, right? So each intermediate value of the matrix could require looking at n intermediate, each value, each position could require looking at n intermediate values. So though the table is of size n square, the actual complexity of filling the table is of size n cube. Okay, so that's why this is an interesting problem, because it says that you cannot directly conclude the complexity of a dynamic programming algorithm from the size of the table that you're trying to update, because it also depends on the amount of effort you have to take to update each entry in the table.